Bismillahirrahmanirrahim. Welcome to this session on data structures and algorithms. Today's major topic is trees. So we'll be talking about different characteristics of trees, different types of trees, and then we'll be talking about some implementation considerations about trees. So if you're able to recall trees, we started trees towards the end of our previous session. And so let's have a quick recap of what we already know about trees. Tree is one of the most important linear data structures. When we say linear data, it's one of the most important non-linear data structures. So the linear data structures which we have studied so far, they include arrays, linked list, stack, queue, and different other types of things like doubly linked list, etc. So tree is one of the first and extremely important nonlinear data structure, which has a lot of different applications in computer science and beyond computer science. So primarily tree is used to represent hierarchical representation. So when we say hierarchical representation, that means that different components or different pieces of the tree are connected with each other using a parent-child relationship. So then we have a term of ancestors and descendants. So the parents and grandparents of a node are called ancestors, and children and grandchildren and grandchildren and so on are all called descendants of a particular node. We will see, we will have a relook at the same example which we talked or saw towards the end of our previous session. So the first node which controls the entire tree, which controls the entire data structure, is called the root node. And the nodes which do not have any further child nodes, they're called the leaf nodes. So all those nodes which are not the leaf nodes, they're called internal vertices. So siblings are the vertices which are primarily in parallel to each other. They are like they share some common ancestors. And length of a path is the number of edges in the path. Then we talked about depth. Depth is length of the path from a node to the root node. And height is another term which we very frequently use in trees. We'll be using it in our discussions in the complexity part of different algorithms, which we'll study about trees. So height is length of the longest branch of a node. So this was the example which we saw towards the end of our previous session. So this is an example tree. So root node is the top node, which is A in this case. A has two child nodes, B and C. So C has two child nodes, G and F, and so on. So when we say a node, that means one object. And the objects are linked with each other using a line, which is called edge. So the data which we store inside a node is called key. So if you look at this triangular part on the left side, so this is a small subtree which is essentially the left subtree of A. So in this subtree, B is the parent node, and D and E are the child nodes of B, and they're siblings with respect to each other. So the nodes which are at the bottom, which do not have any further child nodes, they are called the leaf nodes. So the important thing is that if you have to measure the height, so height of the tree is essentially the number of edges from the leaf to the root. So leaf, for example, is K. So if you count the number of edges, there are 1, 2, 3, 4. So 4 is height of the tree, which is rooted at A. So we can think of, we can like go around these different examples. So for example, ancestors of H are D, B, and A. D is the immediate parent of H, B is the grandparent of H, and A is the grandparent of H. So descendants of E are the nodes which are dependent on E. The immediate child is I, and M and N are the grandchildren of E. So depth of J is the number of edges from J to the root node. So there are 1, 2, and 3. So depth of J is 3. Height of C, so C is here. So if we look at the number of edges from C to the deepest branch, there are 1, 2, and 3. height of O. So O is the child node, so it does not have any children, so its height is 0. Height of A, which will also be height of the tree. So the number of edges from,
For
yep, go ahead. So number of child nodes from the deepest leaf to the root are 4. So for example, if we start counting from O, they are 1, 2, 3, and 4. And same is the case of height of tree, because height of the tree is same as height of the root node. That is 4. So now the way we implement a tree, we have different methods. So one possibility is that, so the smallest thing which we need to create is a node. So we need to think of a node in terms of its implementation. So for example, uh, there is some data part. So that element is the data, might be one attribute or might be containing multiple attributes depending on the kind of application which we are trying to build using a tree. And then it will be having a pool of child nodes, and optionally it can store parent node link as well. So it's our choice of implementation. Sometimes we implement parent link and sometimes we don't need to implement parent link, and that can be managed without storing it explicitly. So if you look on the right hand side, so there is a node which is root node in this case, that is PVD. So PVD is not a child node of any node and it does not have a parent. So it's root node, and then it contains, it is pointing to a vector, a pool of different child nodes. So in this case, there are 4 children of that node PVD. Okay. So any node in a tree can have different number of child nodes. So a rooted tree, when we say a rooted tree, that means we are talking about a simple tree which has one root, is called an emery tree if every internal vertex has no more than m children. So when we say emery tree, that means that if you look at these 3 examples, so m is different in these different examples. So for example, if you look at the leftmost tree, the number of children at the root are 1, then the number of children at another node are 2, and then the number of children at another node are for the 2. If you look at the tree in the center, so root has 3 children and rest of the nodes also have 3 children except the leaf node and the center node. So if we relook at the definition, that says that a rooted node is an emery tree if every internal vertex has no more than m children. So in this case, the first tree which we have on the left, so over here m is equal to 2 because no node over here, no vertex or no node over here in this tree have more than 2 children. But if you look at the node at the tree which is at the center, so m is equal to 3 over here because the number of children can go up to 3. So some nodes have 3 children, some nodes have 1 child over here. And if you look at the rightmost node, it has some nodes have 2 children, some have 3 children, and some do not have any children. So our condition is that every internal vertex has no more than m children. So m in this case is also 3 because 3 is going to be the upper limit on number of child nodes in this particular tree. And an emery tree with m is equal to 2. So when we only talk about the trees somewhat similar to what we have on the left side. So when m is equal to 2, we call it a binary tree. So binary tree is a very frequent term which we'll keep on using in our today's session and in the coming session. And people use it a lot in different interview questions as well. So a binary tree is a tree where every internal vertex has no more than 2 child nodes. And please do interrupt if you have any questions somewhere at any point during the entire discussion. Okay, now what we're going to do is that we are going to uh, impose an additional condition on emery tree, and we are using this prefix now. And the prefix is full emery tree. So full emery tree is an emery tree where every internal vertex has exactly m children. So now if you look at this tree, when you say every internal vertex, which means that we are talking about a vertex which is not a leaf vertex. So internal vertex is a non-leaf vertex. And leaf vertices are the vertices which do not have any child nodes. So all other non-leaf vertices are called internal vertices. So we are imposing a relatively strict condition that we are talking about a tree whose every internal vertex has exactly m children. So if you look at the tree on the left side, so the first node has two children, this node has two children, and this node has zero children, but this is not an internal vertex. So this is another internal vertex which has two children. So if I try to re-highlight them, so the internal vertices in this tree are these three vertices which I have highlighted as three. They are not leaf vertices, and each of them have two, and two child nodes. So we can say that this is a full emery tree with m is equal to 2, or for this particular m, we can call it a full binary tree. And if you look at the tree on the right side, let's first try to highlight the nodes, the vertices, which are internal vertices. So this is an internal vertex. This is an internal vertex. This is an internal vertex. This is another internal vertex. Rest of the vertices are the child vertices or child nodes. So if you look at the number of child nodes of all these green highlighted vertices, they are 3, 3, 3, and 3. So that means that this is an empty tree. This is a full empty tree with m is equal to 3. Okay. Now, one particular characteristic which we wanted to look at, the full embryo tree. So what we know about full embryo trees are the trees which are where every internal vertex has exactly m child nodes. So a full embryo tree with I number of internal vertices has n is equal to mi plus 1. So and the total number of nodes over here are being represented as n. So this is the total number of nodes or total number of vertices. So total nodes in this tree are n. I is the number of internal vertices. So that's the kind of property which we are trying to establish over here. So if you think of a tree, so it has two types of nodes. It has two types of vertices. Type 1 are the kind of vertices which are children of someone. And type 2 is the type of children which are not children of anyone. So in any tree, this number of type 2 nodes is only going to be 1, and that kind of node is called the root node. So root node is the node which qualifies this condition. So all those nodes which are not child of anyone, their count is 1. Rest of the nodes are going to be child of someone, because this is a full tree. So every node which has some children must be having exactly m children. And all those nodes which have child nodes, they are called internal vertices. So the number of internal vertices is going to be I, and I times m is going to be the number of total vertices which are child of someone. And if we add these two things, that gives us n is equal to mi plus 1. So these are the total number of vertices which a full emery tree can have. If the tree is a binary tree, then m will be replaced with 2, right? So does this expression, or does this property or theorem make some sense? So what we are essentially talking about, the kind of trees are, let me try to quickly draw some tree with m is equal to 2. So this is a tree where m is equal to 2. So in this illustration, what we are trying to do is that we are trying to highlight the types of nodes. So the first type of node are the nodes which are not child of anything. So that's the root node, so their count is 1. Now, if you look at the all other nodes other than the first node, they are child of someone. Question number 1, can they be child of a leaf node? The answer is no, because leaf nodes cannot have children. So all these other nodes of the tree have to be child of some internal vertex. And if number of internal vertex is I, so the and this is a full emerald tree. So each internal vertex means that has some children, and because of that full property, that must be having m children. So the total number of nodes, total number of children of all internal vertices are going to be im, and one additional node is 1. So that makes it the total number of nodes in the tree are mi plus 1. So take a moment to absorb this thing. If there is any question, please let me know. Otherwise, we are going to move forward. All right. So theorem number 2, a full emery tree with n vertices has some number of internal vertices, and number of internal vertices over here are being represented as I is equal to n minus 1 over m. And it has some leaf vertices, and leaves are being computed by this second expression. So let's try to understand this characteristic, that what does this mean or what does it say. So what we have just explained in our previous theorem is that the total number of nodes n, they are same as mi. So mi are the nodes which are children of someone, and then there is an additional node which is not child of someone. A node has a children must have the same number of children. Is this correct, Janan? Yes, this is correct if the tree is a full emery tree. So we are talking about a full emery tree, right? So for this particular type of tree, this is necessary. If it has children, then it must be having same number of children across the tree. And these two characteristics are about the full emery trees, right? So we should just be careful about that, what kind of tree we are talking about. So at the moment we are talking about full emery tree, and yes, you're right. So if you look at this expression, n is equal to mi plus 1 from our previous theorem, so we can just like make some substitutions and we can derive this I. So if I bring this I on the left hand side, so this becomes n minus 1 divided by m. So this is what gives us the number of internal vertices in terms of n and m. So if we know m and if we know n, then we can derive I out of that thing. And what is the number of leaf vertices? So there are two types of vertices in the whole tree. So the whole tree, the total number of nodes or total number of vertices are composed of some internal vertices, which means these are the number of vertices which can have child nodes. And then there are some number of vertices which cannot have child node, and those are the leaf vertices. So we represent them using the variable L. So if I just plug in this I from our previous expression on the right side, so we bring it to n minus 1 over m plus L, and this is what is the total number of vertices in the tree. So in order to derive an expression for L, so what I do is that I take L to the left hand side. This becomes n minus 1 over m. And if we try to simplify this thing, this becomes m times n minus n plus 1 over m. And now like this leaves us with the simplest possible math. You can just take n as common, and if you take this n common from here, so this takes us to this expression for the leaf vertices. So these are like just the kind of mathematical insights to understand more about the trees, or particularly full memory trees, in depth. So same way, a full memory tree with I internal vertices, if I has been given, then we can compute n is equal to mi plus 1, which we know, and leaf nodes can be derived this way. And if we know number of leaf nodes, then from leaf nodes we can compute total number of nodes, and we can compute number of internal vertices. So just like on the lines we have done for the first characteristic, your homework is to verify all other properties, which means that the properties which we are left with now are property number 2 and 3, mathematically as well as intuitively. So try to convince yourself that why that kind of mathematics should hold true at the back end for a full memory tree. So if you do it on your own, this is an ungraded exercise, but if you do it on your own, it should help uh, to brush up and clear your own concepts about embryotries, and particularly full embryotries. Now we are moving to a particular type of trees, which is called binary tree. So a tree where all nodes have at most two child nodes is called a binary tree. So again, the condition is on at most. So that means that in this particular version, we are not really focusing on the full binary tree, which should have said that it should be having exactly two child nodes across the tree. So it says at most, that means that some nodes can be having no child. Those will be the leaf vertices or leaf nodes. Some may be having one, which is allowed in this case, and the upper limit is two because the tree is going to be a binary tree. So each node in the tree can have either 0, 1, or 2 child nodes. So this is the simpler version of the definition. And let's have a look on an alternate equally good definition. That is what we call recursive definition. And that is that a binary tree is either empty, so that's our base case, or is made up of a single node, which is called root. And root has two branches on the left and right sides, and both of them point to two binary subtrees, which means that we have a tree like this. So there is a root node. So it can have a left or right. So if you look over here on this pink tree, so the left side of the root node is this subtree, right side of this node, this root is this subtree. So each triangle is representing a binary tree. So, and this, if we apply this recursively, so on the left and right hand side over here, we have null, and over here we have null. So, and that is allowed because we just said in our recursive definition that binary tree can be empty or is made up of one root, which can point to left and right binary subtrees. So this is in principle and in meanings, it is equivalent to the first definition. So this is what we are defining a binary tree in terms of some other binary trees. For example, if you look at this tree, so is it a binary tree? We just need to verify at the level of
Yes.
every vertex. Yeah, go ahead, sorry.
Yes, this is a binary
Very good,
tree.
very good. And how did you check it?
We have at most two children.
Excellent. Every node has at most two children. So some might be having one, some might be
Yeah.
having two, and some might be having zero. So that if you look at that thing, that condition is true across the whole tree, and hence it's a binary tree. So because these are first visualization of the tree, so we can see that there are three kinds of things which we'll be looking at in our implementation. So there is some data part which we need to store inside the node, and it needs to know address of the left child, and it needs to know address of the right child. So these three things essentially define characteristics of one node. So what is height of this tree? Anyone?
Three.
Its height is 3. Very good, right? So height of the tree is the number of edges from root node to the deepest leaf. So there are 3 different leaves which are at the equal height. So its height is 3. So let's have a look at the implementation, which you'll be coming across. So in implementation, structure of one node of the tree is somewhat similar to what we saw in doubly linked list. So if you are able to recall what we saw in the doubly linked list, we said that each node should be having a data part. And in doubly linked list, we used to have 2 references to the previous and next nodes. So in this case, they are left. So those used to be previous and next. Over here, we are calling them left and right, because we know that each node can branch out into 2 things, and we're talking about the implementation of binary tree. Just imagine, we won't be talking about the trees which have more than 2 branches in this course, but that's not a like difficult thing to implement. The only thing which you will have to change for some tree which has a larger M, you will have to treat the number of pointers or number of references over here. And if we don't know that how many references are going to be that thing, if you want to go for something which is generic enough, so you can create a vector of size M over here. So that vector will be containing references to M children, and that will help us to build an memory tree with having a larger number of child nodes at each node. So in the constructor, whenever we create this new node, we set it up to uh, data is set to 0 and left and right children are being set as null. Same way, we can have another constructor which is a parameterized constructor which has 1 parameter. So we can set data over D, and left and right children will still remain null, because we won't be having whenever we are creating a new node, we won't be able to know that what should be the left and right things. But once we know, we can set their left and right nodes using these methods. And if needed, we can retrieve their left and right children, that who are there on the left and who are on the right, using these 2 methods, which will be returning a reference of type node. Or we can return the data stored inside each function using this method called getData. So this kind of skeleton will be quite useful for you to implement a binary tree, or any other kind of tree which qualifies the requirements of binary tree. We'll be talking about some specifics in a while. So within the tree class, there will be somewhat very on the similar lines as those of a linked list. We need to have one specialized node which will be taking control of the entire data structure. So we call it a root node. So root is the reference of type node pointing to the first node of the tree. And then we can use these methods of inserting a node repeatedly to build up the tree. We can use the method to remove the node, or we can search a particular node if we know the data. So this is how the skeleton of the class tree will be looking like in terms of your Java implementation. Now, the important thing which we didn't talk about much so far in our in this code and in the skeleton is that how to display the tree. So displaying a tree is a bit tricky because it's not a linear data structure. So in the linked lists or stacks or queues, we used to like start from one endpoint, go to the other endpoint, and just scan it once, and we are done with the display part, or we can print those things on the screen. So traversal techniques, we mean by traversal technique, we mean that how we can walk through the tree, how we can access different nodes. So because the non-linear data structure, then there could be different ways to walk through the tree. And those are the kind of techniques which we are about to understand right now. And then we'll be in the next slide set, we'll be talking about their algorithms. So the famous traversal techniques of trees are called pre-order traversal, post-order traversal, in-order traversal, and level order traversal. So let's try to understand all four of them one by one. So this is an example tree on the screen. So let's start with the pre-order traversal. So if you look at the smaller structure, so let's start with the smaller structure. Let we have only three nodes in that assumed tree. So let's say I have two over here on the top, and we have something on the left, and we have something on the right. So let's say I have one over here, and I have five here on the right side. So there are only three nodes. There is one parent, there is a left child, there is a right child. So let me characterize them more explicitly. So there is a parent, and it has two child nodes. So there is a left child, and there is a right child. Okay, so the pre-order traversal advocates that parent should be traversed first. So we start with parent, and then we go to the left child, then we go to the right child of that parent. So PLR is the order which is maintained over here in pre-order traversal. So pre essentially means that parent has to be processed first. In the post order, the order of children remains same. That means that left child will be processed first, right will be processed next, and the parent will be processed at the end. So the position of processing of the parent node will change, and then that will be making it post order. And in order traversal says that we need to process left child first, then we need to process the parent between left and right children, and right child will be processed at then, and that makes it in order traversal. So the level order traversal is the kind of thing which we'll be seeing in a while. So let's first focus on these first three traversals, that how these orders which I've just written on the screen are being held true on this green tree, and how things are being printed on the screen. So if you only focus on pre-order, that means that the left child is going to be processed first. Sorry, the parent is going to be processed first. So the first output is one, right? So we get one over here. The second thing is that two has to be processed, but two now has two roles. It's left child of one. At the same time, it is parent of four and five. So from the perspective of four and five, it has to be printed before four and five. So two gets printed next. So then we go to the left child of two, and we check if it has left or right children. So in this case, both of them are null, which means that they don't exist. So as they don't exist, so it's turn of four. So four is printed next. And after printing four, we are done with its entire tree because it does not have further children. So this whole branch is now done. So we were into the process of pre-order, which means that parent has to be processed first. Now its left side has been completely processed, and we go to the right side, which is right side of two, which is five. So five can potentially be a parent of left and right children, which do not exist in this case. So five is printed next, and we don't have any left or right children. So this whole branch, which is right of two, is also done. But as once we are done with the whole branch or whole subtree rooted at five, that means that we are actually done with this whole left subtree of one. So one was printed at the start, now its left side has been completely printed. So if you recall that PLR thing, so parent, then left, and now it's turn of the right side. So we go to the right side. So on the right side, we have three. Three is parent of six and seven, so it is printed next. Then we go to its left child, that is printed, and the whole branch is over. Six is printed, then we go to the right side, seven is printed, and this whole right branch is now over. Okay, so for the next few moments, we should only focus on pre-order traversal. Are we completely okay that how we are doing this whole pre-order traversal? Understanding it important from many perspectives. One is that other traversal techniques are somewhat similar to this one. So if we understand it completely, rest of the techniques will become easier for us. Second reason is that after a while, we'll be writing or designing algorithms for this logic. And the third thing is that our assignment 2 is based on these techniques. So we should be quite comfortable with this whole order of traversal. So pre-order means that parent has to be processed first, then left child, and then the right child. Any questions so far? So if no questions, so what we can do is that we can now go for the second order traversal technique, which is post order. That means that left and right children are going to be processed first, and then the parent is going to be processed at the end, which means that parent will be processed after its left and right children are completely processed. So we start with the root node because that's the only start point we can start with. So we go to its left child. Left child cannot be processed immediately because it is parent of 4 and 5. So we go to 4 and we check its left child, that does not exist. We check its right child, that does not exist. So it's now turn of 4 to be processed, and 4 is the first item which is processed. Then we go to the right side of 5, right side of 2, which is 5. We check its left side, we check its right side, they don't exist. So 5 is printed. So once 5 has been printed, that means that we know that both of the children of 2 have been processed. So now left and right have been processed. So it's turn off the parent. So 2 gets processed next. And once the 2 has been processed, then this whole left subtree is done. So left side has been completely processed. So as we are into the post order thing, so parent's turn will be at the end. So we'll go to the right side, which is 3, but 3 is a parent of 2 further nodes. So we go to its left child, which is 6. We check its left and right children, they don't exist. So 6 gets printed. So we are done with this part. So then we go to the right side of 3. We check its left and right children as they don't exist. So 7 gets printed. And now left and right sides of 3 have been printed. So it's turn of 3 to be printed. And once 3 has been printed, then we are actually done with this whole subtree, which is the right subtree of 1. So once the right subtree of 1 has been printed, now we can safely process this parent itself, and 1 is printed at the end. So this is what is called post-order traversal. Any questions so far? Okay, now let's go to the in-order traversal, which is the third traversal technique. So in-order traversal just switches the order of parent, left and right children. So it says that start with the left child, then process the parent. So parent is essentially processed between left and right children. And that's what this name in order means, that parent is sandwiched between the processing of left and right children. We start with 1, go to the left side, go to the further left. So we check its left, that does not exist. So now as it does not exist, so it's turn of the parent. So 4 gets printed. Then after processing the left side, it's turn of the parent. So 2 gets processed next. So 2 is printed. So after printing the parent, we go to the right side, which when we go to the right side, we check its left and right. They don't exist. So 5 is printed itself. And once 5 has been printed, then we are actually done with this whole left subtree of the whole tree. So once the left side has been printed, then it's turn of the parent itself because it's in order. So one gets printed next. And then we go to the right side of 1, which is 3, but 3 is a parent. So 3's left is 6. 6 is printed next. Then the parent 3 itself is printed, and then at the end 7 is printed. So as a result, then we are done with this whole right thing. But this time right has been processed at the end. So left, then the parent itself, and then the right side has been printed. So this is what is in order traversal. Any questions so far? Okay, the last traversal technique is called in order. It's called level order traversal. So level order means levels are, so this is the level 0, then this is level 1. So these horizontal sibling relationships are defining the levels. So we start with 1. So 1 is printed first, we can see here. Then we go to the next level and we start things from left to right. So 2 is printed first, then 3 is printed. Then once we are done with that, then we go to the next level and we keep on moving from left to right. So 4 is processed next, then it's 5, then 6 and 7. So 4, 5, 6, 7 get printed next. So this is what is the level order traversal. So keep all these visualizations in mind, and we are going to uh, get into the algorithmic details of all these traversal techniques in the next few minutes. So let's take a 5 minutes pause and then we'll resume our stuff from here. You will stay connected, but let's take a small pause. But if you have any questions, I can take the questions and we are going to resume in a while. Okay, is everyone clear about what we saw about the traversal techniques visually? Uh, If there are any questions, we can talk about those questions before we proceed. Um, okay, now assuming that we are comfortable with the visualization of these traversal techniques, and we know that what is the kind of order or strategy which is being followed while displaying the nodes of the tree. So we have to convert the just our visualizations into a program. So in this lecture, what we're going to do is that we're going to write generic code, which means that that's not the language dependent code, and we call it pseudocode. So the first algorithm is for pre-order traversal. So pre-order traversal means that we need to define a function or method whose name is pre-order. A node is passed, a reference of a node is passed to the pre-order function. So the first thing which it does is that it prints the node, which means that it prints the data of that node. In terms of Java, it could be system.out.print or .println node.data. And once the node has been printed, then it checks that does it have a left child. So we just check that node.left is not null. If it is not null, we call the same function on node.left. So this is a recursive approach. So we're calling the same function on node.left, and the same thing happens for the left subtree. But if it is null, then this condition is false and it will skip, will move to the second condition, which says that if node.right is not null, then do this thing for the right subtree. And if that is not true, then it will just stop. That means that this function was called on a leaf node and it just printed that node. It does not have a left child and right child. That's what it means by having those two conditions as the false conditions. So please take a moment, absorb this pseudocode and this logic. It is like, it's a beautifully ordered recursive approach that we are treating one node itself, and then we are delegating the responsibility of processing its left child and right child recursively to another function call of the same function. Uh, any question till this moment? So if not, then I can pause the recording for a while, but I would strongly give you a small exercise that can you slightly modify this code to devise the logic for post order and in order. So take 2 minutes to think of post order and in order after having a look on this code. This will stay in front of you on the screen, but take a moment to derive post order and in order traversal techniques on your own in terms of code by looking at this code. And for all those people who will be watching it later, they can just pause the video and try it on their own to strengthen their concepts. So if you focus on the order of things which are happening in pre-order, that parent is being processed first, and then the same thing is being delegated to the left child, and then to the right child. So you just need to switch the order for the other technique, which is post order. So by post order, we mean that the parent has to be processed after its left and right children have been processed. So what we do is that we start the post order algorithm with, we check the left node. If it is not null, then we process the left node. We call the same function on left child. Then we check the right child. If it is not null, then we call the same function on the right child. And at the end, we land onto the node itself. That means that the parent node is processed at the end. So if you've noticed in terms of code that we've just shuffled the lines of the same logic which we saw in pre-order. And that is giving us the post-order traversal strategy. So if we move forward for in-order, so in-order traversal is again the switching of the same lines of code. So we must first process the left child. So if it is not null, we process the left child first. Then the node itself is printed before we go for the processing of right child. So right child is processed after the node itself has been processed. And that's what is making it in-order traversal. Now, the level order traversal is little different, and let's go for that logic, that how does it work. So if you just have a look on the overall structure uh, of the algorithm, that shows us that it uses something as a fundamental building data structure, and that is a queue. We can see an operation NQ and DQ being used at different times. So that means that in order to get a level order traversal, we need to use a queue at the back end. So let's go with an example. So let's say we have a tree which has root called labeled as 9. Then we have some left child which is labeled as 5. We have a right child which is, let's say, labeled as 6. And then we have some left child which is labeled as 1. We have a right child over here which is labeled as, let's say, 8. And we have our left child of 6 which is labeled as 4. We have right child of 6 which is, let's say, labeled as 2. Now, if you, without looking at the algorithm, if you just recall what did we mean by the level order traversal a while ago, we said that we will start with the first level, so 9 will be processed first. So our first output should be 9. Then we'll go to the second level. So our first output on the second level is going to be 5, then 6. So we're actually moving this way: 9, then 5, 6, and after 6 we'll go to 1, then 8, then 4, then 2. This is what we meant, somewhat like zigzagging kind of thing across the tree. And we're processing things from left to right order. So that's what we meant by the term called level order traversal. So let's get into the depth of the algorithm, that how things are working. Okay, so it starts with a queue. So queue has been initialized with an empty set. So this is a free symbol, which means that we are talking about an empty set. I hope you are familiar with the notation of sets. So queue is an empty set, which means that queue has been created. Name of the queue is queue, and that is an empty string. The first thing which you do is that, so capital Q is an object of the queue data structure. And when we have the queue data structure, that means that we have NQ and DQ supported operations available over there. So first thing which we do is that in our queue, so what we do is that so let's say we have this empty queue at the start. So our level of processing is this way. So we'll be pushing things from left to right, and then the thing which you need to DQ will be processed on the right end. So first thing which we NQ is root itself. So in this example, root is 9. So 9 goes inside the queue. So the first thing which goes in the queue is 9. So after doing this step and queuing 9, we have a while loop. We check the condition if queue is not empty, and queue is not empty because we have just enqueued the root. So we get into this loop. So all these lines are inside the while loop. So what we do is that we dequeue an element from the queue. So element which was enqueued first will be dequeued first. So first thing which is dequeued from the queue is 9. So 9 goes out of the queue and we store it in a temporary variable whom we are calling u. So u is a temporary container. It contains this element which we have just removed from the queue, and there is 9 in our case. So what we do is that we print 9. So let me try to write this output on the screen, that the first thing which is printed is 9. And then what we do is that we check that if 9 dot left is not null, so 9 does not have a null left, so the condition is true. So what we do is that we enqueue this u dot left to q. So u was 9, u's left is 5, so 5 is now enqueued in the queue. So the next item which goes inside the queue is 5. And then we go to the last if condition that says that if u dot right is not null, then enqueue that element. So right side is 6, so that also gets enqueued. So 6 is the next item which goes in the queue after 5. Loop goes back to the while condition. It checks that if the queue is not empty, which is not empty, so it dequeues an element. So as it dequeues the element, so next element which we can dequeue from the queue is 5. So 5 goes out of the queue, and as a result, it needs to be stored in U. So it goes in U. So now next thing which we do is that we print U. So that means that we print 5. And then we check left of 5. So left of 5 is not null. So that is 1. So that means that we can enqueue 1 in the queue. So 1 goes inside the queue. And then we check right of 5. That is 8. So that goes inside the queue. We go back, we check the condition, queue is still not empty. So we run that dequeue operation. So the next element which is dequeued is 6. 6 is dequeued, and 6 goes in the space which is called U. So U becomes 6. So what we do is that we print U. So 6 is printed on screen. And then we check left of 6. If it is not null, left of 6 is 4, so it is not null. So what we do is that we enqueue 4 in the queue. So 4 goes inside the queue. Then we check right of 6, which is 2, so that's also not empty. So we enqueue that thing as well, and we go back to the start of the loop. When we go back to the start of the loop, we dequeue the next element, which is 1. So 1 goes out of the queue, and we place it inside U. So U gets overwritten with what we have just removed from the queue, and that is, sorry, that in our case is 1. So what we do is that, so one has to be printed because it is U, so U needs to be printed. So 1 gets printed on screen. The next thing is that we check left of 1. So now things are a little different. 1 is a leaf node. 1 dot left is null. So that means this condition is false. If it is false, then this queue enqueue operation won't be run. Do we do the same thing for the right side of 1? And that is also not true. So this enqueue operation won't be executed. So we'll go back to the start of the loop. We'll check the queue. It's not empty. So what we do is that we dequeue the next element. Next element which is about to be dequeued is 8. So 8 goes out and it gets replaced inside U. So U now contains 8. We print 8, print U. We check left of 8, which is null. We check right of 8, which is null. So enqueue operations of both conditions won't be executed. We'll go back to start of the loop. We'll check the condition. Queue is still not empty. So what we'll do is that we will dequeue another element. So 4 is dequeued. So once 4 has been dequeued, then we need to overwrite U with 4. So it becomes 4 and it gets printed on the screen. We check its left and right sides, both conditions are false, so nothing is going to be enqueued. And we go to the start of the loop, check Q is still not empty because 2 is there, so we get into the loop. 2 is dequeued, So as 2 is dequeued, it overrides 4 inside the queue. So 4 goes away, and the element we get inside U is now 2. So 2 goes in U. So we print 2. And we check left and right children of 2. Both of them are null. So conditions are false. So nothing is enqueued. We go back to the start of the loop. So this time when we check, well, queue is not empty. So queue is actually empty because all elements which we had inserted inside the queue have been removed one by one. So this will be the stop point. And as we stop over here, so if we try to look on our visualization, the kind of analogy which we were trying to focus on at the start, that how things should be printed in level order traversal. So we started with 9, we moved to the next level, and then we kept on doing this zigzag kind of thing. So 9, 5, 6, 1, 8, 4, and 2 have to be printed. And that's what has been actually printed by this algorithm towards end of the screen. So this algorithm is also called, it has an alternate name that's called breadth first traversal. So we are actually moving things in the breadth. So this is called breadth first, and most probably we'll be talking about this algorithm once again in a slightly different context towards end of the course after a couple of weeks. So this is called breadth first algorithm as well. Okay, again, I'm going to pause the recording, take a moment, and try to understand it, what we've talked about so far. If there is any question, please feel free to let me know. Okay, so we're done with traversal techniques. So now we are going to start with a special type of binary trees that's called binary search trees. So a binary search tree, as the name suggests, is a binary tree with some additional conditions. So in this course, we'll be using this acronym BST very frequently to notate binary search trees. So for all nodes on the tree, the following two conditions have to be met. Key of the left child is smaller than or equal to that of the parent. So by key, we mean the data stored inside the node, inside the left node should be smaller than that of the parent, and key of the right node is always greater than that of the parent node. And if this whole characteristic is true for all nodes, then that tree is called a binary search tree. So question number 1, is it a binary search tree, which you can see on the screen? Very good. Yes. So for all nodes, we've just checked that left of 5 has to be smaller than 5, right of 5 has to be greater than 5. And this should be true for all nodes. So we need to check for 3, we need to check for 8, and for all of the nodes who are not leaf nodes. So it's a binary search tree. Now, if you look at these two examples, so left side is a binary search tree, right side is not a binary search tree. Why left side is a binary search tree? Because it holds those two characteristics true for all nodes. And the reason the right side is not a binary search tree, what is the reason? Any guess that why the right side is not a binary search tree? The reason is that 2 is a grandchild in the right side, in the right subtree of 3. So this side is the right subtree of 3. So anything which is going on the right side of 3 has to be greater than 3. So 2 is the left sub is part of the right subtree of 3, so it cannot be held true. So that means that those two conditions have to be held true across the whole tree, like child, grandchild, grandchild. So the right sub branch of 3 contains the whole subtree which is rooted at 6. So this whole subtree which is rooted at 6 is the right branch of 3. So anything which is going to be on this branch has to be greater than 3. And 2 is the violation point. So that's why it's not a binary search tree. Okay, let's have a quick look on the implementation perspective that what kind of stuff will be expected. So structure of the node will remain same as that of a simple binary tree. So it has a data part and it has two references left and right. So then we have a constructor, we might be having a parameterized constructor, and then we have simple methods to get and set different parameters or different attributes of the object of class node. The class binary search tree will be looking like this, that it will be having a root node, which is again in skeleton. It is very similar to what we saw in a binary tree. So on top of these three things, we might have to implement those traversal techniques inside the class, the same class as well. So there is a root reference, which is going to control the uh, whole tree. And then we can use this function of insert node again and again to insert different nodes inside the tree. And the kind of thing which this insert node has to follow is very important, because there's a particular criteria that who has to go on left and who has to go on right, because this time we are talking about a binary search tree. And the relationship between different nodes is based on the data, based on the key which is stored there. Okay, the question number one, is this a binary search tree? Answer is yes, and very good, because it's a binary tree, which means that the maximum number of nodes which each child can have is 2. So by chance, in this example, every node has only one child, and that's fine. So it's a binary tree, and we just need to look at the other two characteristics, as there is no left child of any node, so that left characteristic does not hold over here. So for the right thing, so 20 is right of 10, that has to be greater than 10. 30 is greater than 20, 40 is greater than 30, and 50 is greater than 40. So it fulfills all those conditions of a binary search tree, so hence it's a binary search tree. So our first task is that how to process for search. So if we call the function search, so we start with the root node. We compare the root.data, root.key with 10, which is our search item. If it matches, we are lucky, and that could lead us to our best case possible scenario where the search operation is finishing its stuff very quickly. So we search for 10. If we search for 9, what will happen? So we'll just compare 9 against 10. 9 is smaller, so 9 has to be on the left side of 10 if there is something. So as we try to go on left side of 10, that is null. So 9 cannot exist. We don't need to compare it with the rest of the items inside the tree. Or if we have to search for 1, again, 1 is less than 10. So if it has to be there in the tree, it will be on the left side of 10. We don't need to compare it with the rest of the elements. So these three examples are the examples of the best case scenarios of the search operation, where our search results can be answered very quickly by chance, by luck, because of those particular keys which we are looking for. And we call it a best case scenario, and we notate its complexity as big O of 1. Versus if we have to search for 50. So for 50, again, we start with the root. We compare 50 against 10, and 50 is greater than 10. So we go to the right. So we check with 20, it's greater than 20. So go on further right. We check against 30. We go on further right. We check against 40, we go on further right. And in the last node, we are successful, and we return true that 50 has been found over here. Now, if you look at this particular example, we have essentially compared every node of the tree with 50. So, or just think of 80 being searched. We start with 10, we keep on moving towards right, right, right. And when we reach to 50, we again try to move towards right, but that is null. So again, we have scanned all items in the tree in the search of 80. Or if I search for 99, the same thing will keep on moving forward. So that takes us to the worst case scenario, where we have to compare all elements exactly once. So that means that we are ending up to big O n, and that's our worst case complexity of the search operation in a binary search tree. And our best case complexity is big O1, which we have just seen for the kind of scenarios which are listed on the left side. Okay, now given this binary search tree, our task is to insert 15. So let's go over that how insertion operation will happen. So if we try to insert 15, first thing is that we go to the root, we go to 10, and we check that if 15 has to be inserted where 15 should go. So as it is greater than 10, so we'll go on right. So as we go on right, we compare 15 with 20. So 15 is now smaller than 20, so we have to go on left of 20, and we go to 12. When we go to 12, we compare with 15. So 15 has to go on right of 12, and that spot is available. So we just insert 15 over there and we are done. So 15 gets added on the left side of 12. So now let's try to insert 2 in this tree. So again, we start with the root node, which is 10. So we compare 2 and 10. 2 is smaller than 10. So we should go on the left side of 10. So on the left side of 10, we have 7. So we compare 2 and 7. So 2 is smaller, so we go on further left. So that left side is 4. So we compare 2 and 4. So 2 has to go on left of 4, and that space is available. So we just get 2 added over there on left of 4. So that's how the tree will be looking like after doing these two insert operations. Okay, now as we are done with the insert operation, so we can have a quick comment on the complexity, that what will be the amount of time which will be required to add something into the tree. So this is somewhat very similar to search. In the best case, we might, if you just think of that linear tree growing only in one direction, 10, 20, 30, 40, 50 kind of tree, which we have just seen in our previous example. So if I try to insert 2 over here, I can get that 2 added just on left of 10 very quickly. So our best case scenario is going to be big O 1. But if I have to add 100, so I will have to crawl through the whole tree and insert 100 towards right of 50. That means that in the worst case, we'll have to go for big O of n operations in insert. Okay, now the third main operation is that how to delete an element from the tree. So let's try to delete 7. So by deleting an element, the first thing which is that we just need to find the element. So we'll do something very similar to what we did for search operation, that we start from the root, we locate 7, that where is 7 inside a tree. So because 7 is going to be a node, so it will be a root node for some subtree. So 7 is the root node of this smaller subtree, which has 4, 9, 2, and 5 inside it. So inside this whole thing, what we do is that we try to find the largest element in the left branch, or we find the smallest element in the right branch, and we swap that element with 7. So that is step 1 of delete operation. So if we try to find the largest element in the left branch, so that is that we will go one step left, and then we'll go to the rightmost part of that subtree. In that case, that is 5. So 5 and 7 get swapped. So 5 goes on top, 5 replaces 7, and then we disconnect 7 and we get rid of it. And this resultant tree is the tree which we get after deleting 7. Let's go over some more examples. So let's try to delete 4 out of this tree. So the first thing is that we locate 4, that where 4 should be, or where is 4 inside the tree. Now we go for we try to find the largest element in the left subtree. So left subtree of 4 contains only one node, and then that node is going to be the node of that node is going to be the largest node of left subtree. So what we do is that we sort of locate 3, and 3 replaces 4. So 3 becomes the right child of 2, and 4 goes away. So essentially 4 goes away, 3 becomes the right child of 2. That's what it meant by removing 4. let's go over one more example. Let's try to delete 2. So we look at 2, and now we have two choices. One choice is that we replace 2 with the largest element in the left branch, or we have another choice as well, and that is that we replace it with the smallest element in the right branch. So we'll go for the second choice this time. So in the right subtree, which is rooted at 5, the smallest element is 3, which means that we'll go one step towards right, and then we'll go keep on trying to move to the extreme left. So there's nothing further left on 3. So this 3 has to be somehow located, because this is the smallest element in the right subtree of 2, and it gets swapped over there. And then we just get rid of 3, and 4 becomes the left child of 5 directly, and this gives us the resultant tree after deleting 2. Okay, any questions so far? So we've talked about the complexity. So worst case complexity of such operation is big O n in binary search tree. Same is the case of worst case complexity of insert operation and delete operation. So all of them take big O n in the worst case. There are some important considerations. So there are factors which affect the complexity. What makes it worse? So essentially, the thing which is making it worse is the height of the tree. So if height of the tree is getting proportional to the number of vertices, then that is going to be having an impact on our complexity of different operations. And then the question is that what will be the ideal kind of worst case complexity, or in other words, what will be the ideal kind of height of the tree? And the answer is that we need to have another kind of tree which is called complete binary tree. So a binary tree which is filled at all possible levels with the last level filled from left to right. That means that we are going to compact many nodes into a smaller height. That's called complete binary tree. And height of the complete binary tree is proportional to log n. And log n is a much smaller number than n itself. So if the complexity of all of our operations is dependent on height of the tree, then having a compact height of the tree, keeping a mechanism to keep the height compact is going to help us a lot in reducing the time complexity of different operations. So what we'll do is that we will restart our next session from this point, and that will take us to another kind of tree which is called avial tree. So that's a special form of binary search tree, but generally, like, we're done with binary search tree. So let's have a quick look at the traversal techniques. So once you go back, try to find out the output of the traversal techniques of this thing. So particularly if this is a binary search tree, so in-order traversal is going to give you something special, and try to figure out on your own that what is that special thing which will get if you apply in-order traversal on a binary search tree. Okay, the last thing which I wanted to share with you is that assignment 2 is going to be uploaded soon. So the idea of assignment 2 is that you will have to write a Java program to implement binary search tree from scratch. So you'll have to implement the node class and then a BST class. So your implementation is expected to be supported by all methods to add, remove, and search the nodes. And you will also be required to implement all these 4 traversal techniques whose algorithms we have just studied. So I just want you to uh, get into the depth of all these things in terms of code as well. So it is strongly recommended that do individual work. And it is very important to understand and implement this assignment for 2 major purposes. It's like interview questions are very common in the industry, particularly software industry, as far as binary search trees are concerned. And the second important reason about this particular assignment is that assignment number 3 will be dependent on this code. So if you don't implement assignment 2, it won't be possible to start assignment 3. So these two assignments are quite interlinked with each other. So I would strongly suggest that start this assignment on time, complete it on time, and that your code will help you yourself. Besides marks, it will help yourself to start assignment 3 in an easy and good way. So please do work on it and complete it on time. So that's it for today. Thank you very much.